We're in time. Welcome back and welcome new audience in Arena. I'm very happy to present you with Sheila A. Berta. Sheila A. Berta is probably the least known black hat speaker in Switzerland. She actually lives in Bern, Halvier, and it took me years to notice that she's actually living very close from us, and I thought we absolutely need to have her here on stage. She was reluctant because she said she wanted to do new research and she was not sure she had the time to do. And then during summer she came back, no, I think I have something. These honeypots, they're much too easy to identify. Please welcome Sheila on stage.
Thank you very much. Hello everybody, and thank you for attending this talk, and thank you, Chris, for the introduction. And thank you for inviting me, because it's really nice to be here. I'm very happy to sharing this research today. I'm looking for the clicker, if everybody knows where it is. Fantastic. Otherwise, I will not be able to progress here. Super. So, yes, I'm Sheila, and I'm an offensive security researcher with more than 15 years in the field. I started very young, like at 12 years old. Very crazy, but yeah. And I work as head of research at DreamLab Technologies. It's a Swiss company based here in Bern. And I'm part of the review board of Black Hat USA. Maybe you hear about that conference, huge conference in Las Vegas. Well, I'm part of the academic committee that chooses the talks that we will present there. And I've been a speaker as well at Black Hat briefings, DEFCON Main Stage, Hack in the Box, and other technical security conferences. And now Swiss Cyberstorm as well. Okay, so today I will talk about how to identify honeypots, new ways to identify honeypots, or novel ways. But first, let's take a quick look or quick review of what honeypots are and how they work, just to make sure that we are all on the same page. And then the main topic of the talk, how to detect honeypots abusing these flawed logic issues. Then we will see what this is. And finally, some statistics and a counterintelligence example. So, honeypots. Honeypots mimic real systems to attract attackers. They can be vulnerable systems on purpose, or just services connected to the internet waiting for being attacked. But it's a trap for the attackers. So the idea is to allow defenders to study the attacker's TTPs, or tactics, techniques, and procedures. So every movement or interaction with the honeypot is recorded or logged for further analysis. So the goal is to gather threat intelligence statistics, some way, maybe improve the detection mechanisms, like, for example, creating a Yara rule to detect a new attack that was identified in the honeypot, right? So that's the use case. The architecture usually looks like this. The attacker interacts with the honeypot that is mimicking a real service. It could be a database, a web server, SMB server, whatever. And behind the honeypot is usually a stack of technologies capable of processing the logs, the attack logs, and then show the information in a nice way to the defender. The elastic stack is very common in this setup. For example, Teapot is one of the most popular honeypot frameworks, open source, and they use the elastic stack and Kibana to show the information to the blue teamers. There are two major categories of honeypots: the real services and the emulated services. Both have its pros and cons, let's say. The advantages of using real services is that you can expose like the full capabilities of the service. I mean, allow the attacker to interact with all the functionalities. And of course, a real service is a real service, so it's quite more difficult to detect that the real service is being used as a honeypot. However, it requires a high effort to create a real service as a honeypot, because real services are not prepared to function as a honeypot. So the logging is complicated, the maintenance is complicated, you might need to redeploy the honeypot every time that is compromised, among many other constraints. So people usually prefer to use emulated services because they are ready to use. I mean, these honeypots, they are services that are prepared to work as a honeypot. So the logging is clear, the maintenance is very easy. They are usually open source and free, so very low effort there. However, their capabilities are quite limited because, after all, it's an emulation of the service. It's not a real service. So maybe not all the functionalities will be available. And also, they are vulnerable to flawed logic issues, and we will use them to detect these honeypots, as we will see later in this talk. So the emulated services are the most popular ones. Teapot, Ionia, Compot, there are many open source frameworks of honeypots, and they are the most common implemented worldwide at the time of deploying a honeynet. A little bit more of information. People tend to associate real services with high interaction honeypots and emulated services with low and medium interaction. This is not entirely true, or not necessarily that way. Because we could have great emulation of services, allowing a lot of interaction, and they are still an emulation. And we could have, on the other hand, real services limited on purpose, allowing a very low interaction. So the level of interaction of a honeypot refers to how much the attacker is allowed to interact with the honeypot, and not whether it is a real service or an emulation, just to clarify that concept. OK, so let's start with these flawed logic issues, or a different way to detect honeypots. First of all, I'm not the first person trying to detect honeypots. So let's take a quick look at the previous work. So previous research were focusing on a bunch of techniques to detect honeypots. There are a few white papers out there that you can check out. So summarizing the idea, or the previous work is based on these techniques. First of all, the most common one, the full service banner analysis. You know, when you connect to a service, it says hello and shows some information. So the honeypots have like a static banner. So the easiest way is to take this banner as a fingerprint. That's the most common. Then maybe some default response to certain commands, maybe the content of a file or the response to a command. The certificate configuration, this was one of the latest research I saw on honeypot detection, that people were analyzing the issuer and subset and trying to detect some default configuration in certificates. That was quite interesting. And then some suspicious behavior, like too many open ports in the asset. This is a common behavior in honeypots. Or, I don't know, using a cloud provider to host an ICS honeypot. That would be not really normal in real life, right? So previous work was focusing mostly in these techniques. So I wanted to come up with something new, or something a bit more sophisticated to prevent the counter detection techniques that we saw before. So I wanted to detect honeypots based on a flawed logic in their packet handle functions. Basically, it works this way. We send a malfor or unexpected packet to the honeypot, and then the honeypot doesn't know how to handle that and responds with an error or in an unexpected way, or different from a real service. So we use that as a fingerprint. This will help to bypass the countermeasures that we saw before, because it doesn't matter if you customize the banner, the certificate, the static response of a command, because this is a flawed logic issue in the honeypot. So you might need to patch the honeypot code to fix that, and that might be much more complicated. And also, I limited myself in this research to a minimal interaction with the honeypot, only 1 or 2 packets, because after all, it's a trap. We don't want to interact too much with it, right? So I wanted to identify some flawed logic in the first packet, in the first connections. Also because I wanted to run a large-scale analysis. The less the interactions, the faster it's going to be. Cool, so let's start. Some common services first. The Ionia FTP emulates an FTP honeypot. The request, this one is very simple, so it will help you to warm up. We send a line break as a password, and the honeypot responds 500 syntax error pass requires an argument. If we compare this to a real FTP server, here we have Pro FTPD. If we send a line break as a password, it responds with a 530 login incorrect. And if we send a bye, it responds with a goodbye. This is a real FTP server. Now, back to the honeypot. If we send a line break as a password, it responds with a syntax error. Pass requires an argument, and if we send a by, it responds again with another error. So this is the idea, just to catch a flow logic and get it as a fingerprint to identify the honeypot. Cori SSH, it was one of the few honeypots that I saw some previous research on trying to find a flow logic, but it was bringing a lot of false positives, so I was trying to improve this one. It's one of the most complicated ones. In this case, we use a wrong version of SSH, 1337, and it responds with protocol measure version differs or bad version 1337. The newest services of OpenSSH respond with a protocol mismatch. There might be some very old version of OpenSSH responding with this bad version, so that's the reason why you might find a few false positives. But most of the honeypots, well, the honeypot itself responds with this message, so we can identify most of them this way. Mail-in MSTP, this is an email server. Very simple detection as well. We send a help or non-existent command, and it responds with a 502 error command help not implemented. If we compare with a real XIN, if we send the help command, you will see the actual answer or the correct answer. That is the command supported. If we send a non-existing command, you will see an unrecognized command message. That's fine. That's the real service. If we now do that with the honeypot, we see that we get this error that the command is not implemented, and the same for the non-existing command. So that was quite simple as well. Dionia HTTP, another popular web server, honeypot, a honeypot for a web server. So I was playing here a little bit with some HTTP requests. There are many requests that respond completely different than a real service, but this one is the most clear one. If you send a wrong method, like AAAA, then it responds a 501 not implemented. If we compare with a real XIM, we see that the actual answer should be a 405, not allowed. But the honeypot responds with a 501 not implemented. And it's still an Nginx, so it's a different way to handle the same error. Something similar happens with the snare. That is another popular honeypot for web services. If we send, in this case, a wrong HTTP version, it responds with bad status line expected dot. So this is a message from the Python script, basically, so it's even worse. Again, if we compare with a real Nginx, it should be an HTTP version not supported, the real answer. If we check the honeypot, then it says this 400 bad requests and the message from the Python script. And even worse in this case, because if you check the server, it reveals that it's a Python script. But I did not rely on that because mostly in the honeypots you can customize the banners. So if you change, you can change that. So I prefer to rely on the flow logic in this case. It's more precise. Dionia SMB, sorry that I'm going in a rush, I don't have too much time. This was a bit more complicated because this protocol is more complex. So we start an SMB negotiation. I did not put the full packet because it's a bit long for a slide. We receive, in the response, we have a string that is kind of hard-coded. Now, in the packet capture, maybe it's more clear. The first line is what we send, like a hello. We start the negotiation, and then in the response, we see that A with E, 8T, that short string, it's always there only in the honeypot. This is part of the SMB challenge that should be random, but in the case of the honeypot, it's not random, so it's always the same. If we check with real services, we see that this string always changes. For every SMB server, it's going to be different. So I was trying to deep dive a little bit in the source code of the honeypot to try to understand why that string was there. And then I found out that these libraries commonly used for honeypots used to hard code the SMB challenge. Because it's not really necessary. I mean, these libraries like Scapy, InPacket are used to debugging mostly, so they don't need this randomness. And they say, OK, if you want to change that, you can edit the source code. But the honeypot uses that way, and modifying in the honeypot is more complex. So that's likely the reason why you see that hard-coded string. So I was using that to identify the honeypot, and it worked out pretty well. Databases, other kind of honeypots and different protocols. Dionia MySQL, we start a MySQL connection, and we receive that very weird string that say, I don't know why, because I have not found that string anywhere else. But it happens in the first network packet that you send. This is a real one. The real one tells you the version, that's completely fine, and then comes a couple of features, could be larger, the response. But in the honeypot, it says the version as well, but then that string that I don't know where it came from, I did not have much time to investigate exactly this AAA, what it belongs to, but it was only found in the honeypot. So I was using that as a fingerprint as well. Cool. MongoDB, this one is awful, this protocol is So we send a build info command, that is a very large command, and then we found that the version is not present, and this is completely wrong for this, for the response for this command. If we check real service, we see that the version for this specific packet, the version is the first thing that you should see. And in the honeypot, it doesn't appear. I don't know why, but it was, I took that to identify, then ran the analysis, and it worked out because I detect that it was not bringing false positives, so only the honeypot. Elastic pot, but this one there was like 1,000 ways to identify it. But I will mention only one or two. This is still emulating a web server as well, so you can play with the HTTP request and also with the real request for an Elasticsearch service. And there are different responses that are not exactly the same as the real service. If we check, for example, if we send a HTTP request with a wrong method to the real Elasticsearch, it says that the method is not allowed. If we do the same to the honeypot, it says this is not implemented, 501, and I cut off the screenshot because below that it says I don't know how to handle that request. So it's completely different from the real Elasticsearch. And also it reveals in the server that is a library being used there. So this is one method that you can use. Or other method is that if you update, just a post request to update any random index, the honeypot will say, OK, no problem. But in the real Elasticsearch, it's not the case. If you try to update a random index, it will not find it, so it will throw a missing exception. The document is not there. That's the real behavior. So, Redis honeypot, this one was very funny. Because if you send a quit command or a non-existent command, it responds the actual message that Redis will respond, but there is a little detail that is that they miss a white space at the end of the message. Look at this. This is a real Redis. If you send a non-existent, you see there is a white space at the end next to the with word. And if you send a quit, it says, OK. Now check the honeypot. If you send a non-existent, that white space at the end is not there. So the devil is in the details, right? So for me, that was useful, because this response, it's a copy-paste of the error, and they miss this white space. So for the detection, I was taking into account that, and also the response to the quit command that is wrong. Applications, well, these ones are a bit different, because we'll see here Cisco and Citrix, but they are running over real web servers, so I was focusing more on the content. So a real Cisco ASA looks like this. It says login, and in the case of the honeypot, it says logon. Just I don't know why I was trying to. I thought that this would not work, so I was running an analysis. But it seems that very, very old version of Cisco maybe had that logon, but they are no longer. You can no longer find them. So the real Cisco had the login there. So well, there was a detail as well. Similar case for Citrix. Well, this one was even more obvious because this is the real Citrix portal, and this is the honeypot. So here the author did not put much effort. But if you take a look at the labels, they all match because it says logon, it's our username and password exactly the same way than the Citrix one. So what I did here was to use the content length. There is a string that says something that terms of conditions that you need to accept, that it's hidden in the source code of the real Citrix, so it's not there in the honeypot either. ICS Compot is the most popular framework for honeypots for ICS. The Compot emulates different services, so I used Siemens because it was the easiest one. If you send a first packet, it always responds in a way that is not really normal in Siemens. I was trying to compare with real services, real Siemens, and if you send these packets, the PLC tends to respond like an acknowledge with the same one. And in the case of the honeypot, it was always different. And I was not able to find a real PLC responding that way, so I used that as a fingerprint. Just moving forward faster. Others, Dionia MQTT. Mosquito is quite popular in IoT devices. This one was a bit complicated because it's just a publisher-subscriber service, so the subscriber doesn't tell you anything. So it was a bit complicated to find something. But I realized that if you use the V5 version, the honeypot is not able to handle it, and it responds like a V3, and then you can detect that it's not responding well and identify the honeypot that way. If we see in the network packet, this is a real service, works perfectly. With the V5, the honeypot, you can see the error there. If we analyze it at the network packet, this is what we send, and this is the response of the real service. And this is the response of the honeypot. It responds like a V3, so it doesn't work well there. So the idea was that you don't manually need to craft every packet that I was working on. So I thought that the best way to automate this will be to create a few Nuclei templates. Nuclei is an open source project that you can create templates to automate vulnerability detection and so on. So I use it for detecting the honeypots. I create one template per honeypot, so they are ready to use. This is an example. The most important part is in the input we send the packet that we saw, like the attacker side. And then in the matchers, we look for the string or the command or the response of the honeypot that we are looking for. Is this a honeypot? So if it's a honeypot, it matches. And I will upload these files to my GitHub in a few days. And let's see a short video demo how to use it. So the templates are just YAML files. So there are many there for the different honeypots. You need to install Nuclei. I will use the debug response parameter to have more information. With -u, you pass the target. And with -t, the YAML file, the template. So if it's matched, you will see the green, because it found the binary that you were looking for. And there we can see in the dump that is actually present. Let's run just one more. The MySQL, for example. It sends a quite more large packet. So the challenging part of this research was to find the right packets to send. Or maybe to install the honeypots, right? That was, in some cases, more complicated than breaking them. So now we try to find that AAA word in the MySQL. So let's see. It responds and match both of the words. So it's quite simple to use. I will make available the YAML files, and with Nuclei, just with one click, you can use them. So just 3 slides here. I'm finishing, I promise. Some statistics. I was using SciOps, our cyber radar, to run these templates and get some statistics of Switzerland. There are more than 280 services running on 121 honeypots. Let's discount maybe 20 of false positive of SSH, but around 100 honeypots in Switzerland. There are more services because every server of honeypots run usually more than one service, so it's normal. Across 14 cantons, then you have the heat map. Of course, Zurich is the one that's running most of the honeypots, then Geneva, Bern, Ticino. And then the organizations, most of them are cloud providers or behind some IP addresses of different internet service providers. But there are a few organizations that are running these honeypots inside their network, their own network, so that allow us to do some counterintelligence. And for example, the Center of the Cálculo Científico in Ticino is this entity. I don't know how popular it is, but it's running also a teapot. We detected that using these templates, we discovered that they are running one of these instances in their network. It's not a good practice, but okay. And then we found a few other universities, but I don't want to disclose too much. Conclusions, well, customized honeypots can still be detected by flawed logic issues. Doesn't matter if you customize the certificate, the banner, the flawed logic is another type of problem and it will be there unless you patch the code. So it's a different way to identify honeypots, more reliable in my opinion. So you might want to use real services, but they are, as we said at the beginning, more complicated to create and maintain. In my team, we created a solution for this, but I don't want to spam. But it requires much more effort. And then please don't run honeypots in your own network, because if they are detected, allowed to do some intel on who you are. And also, I have seen the code of these honeypots, and they are very poorly written, so I'm pretty sure that they have also quite a lot of vulnerabilities. So please try to isolate them the best you can. So I guess that was all. Thank you very much, and I hope you liked it.
Wonderful. Thanks, Sheila. Yeah, but it's perfectly in time. We have time for 1 or 2 questions, depending on the size of the question. Here, please. There was one. Mic is coming.
Thank you very much for the very interesting talk. I have, in fact, 2 questions which are related to each other. First of all is, do you think that attackers, they try to recognize honeypots and then they don't attack them? And if so, for the second question, do you have any statistics of, how many less attacks you get if your honeypot is detectable than if it is not? And in fact, the third question, do you think you could prevent your system being attacked by making it look like a honeypot, when in fact it is not?
Okay. Yes, I think that attackers want to detect honeypots in the simplest way possible. As I say, with the less interaction possible, because if you interact too much, some way it's a trap, so you will be catched. This is just for fun. I'm not an attacker. But one of the reasons why I wanted to identify honeypots is because they alter the statistics. I am analyzing Switzerland. We do that to detect vulnerabilities like showdown or census there. But the honeypots really alter the statistics, because you have maybe very vulnerable assets, but they are not real, they are just honeypots. So that was one of the reasons why I was doing that and trying to identify them. But I think that then attackers have many reasons to try to identify honeypots and reduce or blacklist the IP addresses of honeypots. That will make a lot of sense. Of course, I don't know how much they do that. But it will be quite smart. So I think that maybe not the automated attacks, but I suppose that some more sophisticated attackers really look for this and blacklist or try to not attack, or try to identify. Maybe if they see an infrastructure too suspicious, like to be real, to expose, and to suspicious, they will try to figure out if this is a honeypot or not, I think.
Wonderful. I think we're cutting Q&A here. Thank you very much for your presentation. So glad you made it. It's a bit of chocolate.
Oh, thank you very much. Thank you to you for attending, and thank you, Chris.